Hello everyone, welcome back again to this online Structural Geology NPTEL course, and today we are on a new week and we are going to learn deformation mechanism part 1, where we will study crystal defects and associated structures. And the topics we will cover are mostly an introduction to crystal defects, and then we will classify the crystal defects and describe some of their associated features which are important for studying structural geology and in particular microstructures. We talked about the deformation mechanism very briefly at the very end of this last lecture. It is very important to realize the fact that the deformation that we see, the strain the rocks do accumulate, sometimes these strains are extremely large. So, the question always being asked that what is the mechanism, what is the process by which these strains are being accumulated within the rock mass. And most of the time we see that the entire rock is not getting strained, but it is localized or channelized along a very narrow area or narrow zone, what we call deformation localization. Now, to understand this process, it is the study of deformation mechanism that deals with the various processes of grain and crystal scale deformations which are responsible for deformation and at the same time accumulating the large strain in the rocks. Now, why grain and crystal scale? Why not in outcrop scale or in large scale or tectonic scale? Now, at this time we have to understand the fact that particularly in the ductile domain, any deformation that we see that do initiate at a very small scale, very micro scale to be very specific, and when we talk about the micro scale we actually refer to the atomic scale. So, the deformation do initiate at a very micro scale within the crystal. Most of the rocks, as we know, are crystalline solids, polycrystalline solids. So, it is therefore important to understand what is happening inside the crystal when we apply some sort of stress, how the crystal is accommodating the strain, what sort of features we should see within the crystals which are probably going to trigger a large scale deformation. So, this is the topic of this lecture, and to understand this behavior within the crystal, the deformation behavior within the crystal, we need to understand first what is inside a crystal. Now, we know that a crystal is generally the unit, we call it a lattice, and within the lattice we have the elements which we call motif. Now, when we define a crystal, or what we have learned so far from our chemistry or physics lectures, that classically a crystal is defined as what is written here, a homogeneous solid formed by a repeating 3-dimensional pattern, which is your lattice of atoms, ions or molecules, which are your motifs, and they have fixed distances between the constituent parts. Now, this sounds like that it is very homogeneous solid, or they have equal or fixed distances between their constituent parts, their compositions or individual motifs are very similar and so on. This looks like a very perfect place. Unfortunately, the perfect place inside the crystal hardly exists. What I mean by that perfect crystal, if we talk about, then it does not exist. So, the best crystal that you can think of would have around 1 parts per billion defects. Now, all these defects or imperfections that makes a crystal to deviate from its actual original definition are known as crystal defects, or what is written here, the imperfections within the crystal structures are known as crystal defects, and crystal defects are very important in the deformation of rocks, particularly in structural geology, and at the same time in many other subjects also in material science and other mechanical processes. So, to classify crystal defects, generally people do classify in or 3 different ways. So, the first one we call it point defect, or it is also known as 0th dimension, and examples we will see all of them, vacancy or interstitial. Now, second category is line defect, because it is line, so it is one dimensional, and the examples of line defects are dislocations. And then we have finally surface defects. Surface defects are, as the name suggests, it is a surface, so it is 2 dimensional, and the examples are either free surfaces or various types of grain boundaries. So, in this lecture actually we are going to explore these 3 types of defects. So, first we will take over vacancy, interstitials and so on, that means point defects, then we will go to line defects, and finally we will conclude the lecture with the surface defects. Now, what is point defect? Point defects are places where an atom is missing or irregularly placed within the lattice structure. So, atoms around the point defects are displaced from their equilibrium positions. Of course, if the crystal is not in equilibrium, that means there must be something wrong, and this wrong thing is either one atom or one element is missing, or it is placed somewhere where it should not be. So, therefore, if an element within the lattice is staying somewhere else or is missing, then the crystal always tries to make things in equilibrium, but it cannot do it. So, therefore, there is a local differential stress field that is generated in the neighborhood of the vacancy, and this local stress field is very, very important in determining many processes that primarily includes the diffusion of substitutional atoms, and you can think of many other processes that these vacancies are responsible for. These are climb of edge dislocation, some forms of creeps and increased resistivity. We will learn particularly diffusion and substitutional atoms very briefly in this lecture, but we will learn more later on diffusion creeps when we learn the particular mechanism. But today we will look at how climb of edge dislocations do happen with the assistance of point defects. So, point defects are classified in this manner, what is given in this slide. So, first they classified whether your crystals are ionic or non-ionic, and if your crystals are non-ionic, then you have vacancy and impurity, and within the impurity we have interstitials and substitutional vacancies. Within the ionic crystals, there are mostly 2 categories, one is Frankel defect, another is Schottky defect, and there are few more, but we will mostly look at Frankel and Schottky defect very briefly. But before that, let us go to the non-ionic crystals and first take over the vacancy. So, vacancy that we talked about, as we see in this illustration, that if I look at this area in particular, the atoms within this particular segment of this lattice are distributed very homogeneously. Their interatomic distances are constant and so on. However, if we see this place in particular or this place in particular, one atom or one element is missing. So, vacancies are there for the places where an atom is missing or irregularly placed within the lattice structure. What is important to see that these straight connections that we see where there is no vacancies as such are now somehow distorted, and they are distorting towards the vacancy side. Now, this is where these bonds or these lines, as you can think of, are stretched or deformed or distorted, and these are the places where you generate some sort of differential stresses. So, these are vacancies, and let us talk about the impurities. There are 2 kinds of impurities, as you have learnt. One is substitutional impurity, that means you have a vacancy, but vacancy is not vacant, it is occupied by some foreign atom. So, a foreign atom came, it replaced the parent atom within the crystal. So, this is known as substitutional impurity. And interstitial impurity is when a foreign atom sitting in the void of a crystal. So, somewhere within the crystal it disturbs the lattice structure, but it does not omit or remove any atom from the lattice. So, here this one is an example of substitutional impurity, and this one is an example of interstitial impurity. Now, most of the gemstones that we see or that we are aware of are actually results of substitutional impurities. I give you an example, for example, ruby. Ruby we know is a fantastic gemstone, is red color, but the host mineral of ruby, the actual mineral of ruby is nothing but corundum, it is aluminum oxide. Now, the chromium atom, it replaces, if it replaces 1% of the aluminums inside this corundum crystal, then it becomes red, and that is why it becomes very, very important to us or very precious to us because of this red color. So, it is not a pure crystal that we see as ruby, it is actually a corundum, aluminum oxide, and in one site, the metal site, we have aluminum replaced by chromium, and therefore, we see the red color, and that is why it is expensive. Now, for the interstitial impurity, you can think of the carbon steels that most of our soft steels that we use nowadays, including our cars and so on, the carbons are doped inside the ferrite crystals, which is a BCC crystal, and this you can think of a carbon atom inside a ferrite crystal. So, carbon steel is a perfect example of interstitial impurity. Now, when we learnt about substitutional and interstitial impurities, let us move on to point defects related to ionic crystals. And as we have classified, there are two types of ionic crystals defect. One is Frankel defect and another is Schottky defect. Now, ionic defects, they do occur when one of the atoms in an ionic lattice is simply in the wrong position or missing. In this context, a Frankel defect in an ionic lattice that occurs when one of the ions is in the wrong position. So, what we see here, this is a lattice structure without any defect. So, this is a perfect crystal as you can think of, and then you have some ions with positive charges and some ions with negative charges. Now, what we see here, positive charged ions are missing from this side and they are sitting somewhere here, and the same example you can see, the ion is missing and it is sitting somewhere here. Now, the basic idea or one of the properties of crystals with Frankel defect, which we are discussing now, is that nothing is missing in this frame. So, the number of atoms or number of ions, if we count, these remain constant. Therefore, even if there are vacancies or different type of vacancies, the density of the crystal does not change. On the other hand, a Schottky defect is when you have a pair of anion and cation are missing. For example, as you can see here, this one and this one, an anion and cation are missing from this crystal or this lattice, and again here a pair, always they have to disappear from the system as a pair, and if that happens, then it is known as Schottky defect, and you can imagine that if this happens, then the density of the crystal varies. So, the example of Frankel defect is, you can think of as the example is given here, silver iodide, which is a kind of material or complex, where in this case the Ag plus ion, the silver ion is missing from this actual site and it is sitting somewhere else. And Schottky defects we mostly see in different kinds of salts, where for example here the KCl ion, the KCl salt, where both K and Cl, K plus and Cl minus, they are missing from the crystal. Now, how point defects are important to us? We'll learn more about it, but points defect are if there are some sort of differential stress externally or some sort of disequilibrium, then they try to move from one site to another site. So, if an atom jumps from its lattice site into the adjacent vacant site as it's at its neighborhood, it fills the vacancy, but because there is no extra atom, so it leaves behind another vacancy. So, in effect, that it causes the shift of the vacancy to in the opposite direction to that of the atom. What I mean by this, or reading this text, is explained in this illustration. So, what we see, we have a vacancy here and we have a neighboring atom. Now, if this atom has to move, then the best place to move is to come to this vacancy site. So, what it decides, it moves to this place and the vacancy then comes back to the position of the atom. So, therefore, in the next lap, again the next atom moves to this vacancy site and the vacancy comes back, or vacancy moves to the position of the atom, and here is the same case. So, what we see here, that in this illustration, that vacancies are moving in this direction and atoms are moving in this direction. So, therefore, their movements are opposite. It is very similar the way electricity moves or the electricity goes. So, electrons move the direction opposite to the electricity. So, this is a very interesting idea that we will explore more, and it involves also the volume changes or shape changes of the crystal during or due to the movement of vacancies and atom in the system. But for the timing, we will stop here. We will learn more about it when we learn more about diffusion creep and diffusion mechanisms. Let us move to the next part of this lecture, is line defect or dislocations that we have learned. Now, vacancies, as you have learned, are 0th dimension, that means they are point defects, but line defects are linear defects, and linear defects are commonly referred as, we have learned, dislocations, and dislocations are nothing but the lines through the crystal along which a crystallographic ordering is lost. We will learn more about it soon. So, the dislocations are very, very important in terms of structural geology. So, they are movements and networkings. The movements and networkings of dislocations control many, many things which are responsible for formation of the structures that we see inside the thin sections or even large scale structures. So, one of them is they control the yield strength of the deforming rock. So, strength of the rock is controlled by dislocations and their movements. They also can produce various types of microstructures and subsequent plastic deformations of crystalline rocks. The dislocations also do participate in determining the grain size of the plastically deformed rock. So, a plastically deformed rock has larger grain size or smaller grain size is actually controlled by dislocations, and this happens through a process called dynamic recrystallization. This we will also learn in the next lecture, and it also defines the nature and orientations of the grain boundaries. So, dislocations are one of the most important crystal defects that we deal regularly in looking at microstructures and so on. The dislocations are classified in two segments. One is edge dislocation and another is screw dislocation. Now, we will first look at edge dislocation and then we will understand the screw dislocation. Edge dislocation is much easier to understand and comprehend. But before we go to actual scenario, let us get a concept that what is dislocation. Now, what we have here in this illustration, we have a block, say a crystalline solid, and then by some means we made a cut, halfway cut through the middle of this block. Now, because this would be deforming plastically, let us assume that to understand or to visualize better, let us assume this is a piece of rubber. And then if you push it in this side, the top part only, leaving not at the base, so it would try to squeeze in this direction, but because this part is fixed, so at this segment this material would be much denser. So, eventually it would look like something like this, where this edge of this cut is fixed, there is no displacement, and then along this line everything got slipped along the plane that you made cut, or you can call it a glide plane. Now, this has to move following a vector, and if we consider that this is a vector because you are applying the force in a same direction, so we can term it as B. We will learn what is B later, but this is the basic concept of dislocation, that one side of this cut or one side of this line has got a slip and another side is not slipped. So, this part experienced slip and this part not. Now, because the volume or other things has to be constant, so in this segment you might have some rearrangements of the atoms within the lattice, so that it can accommodate this unit vector displacement within itself. So, the lattice, the atoms, they are arranged accordingly to accommodate the deformation, whether the other part are not deformed or not disturbed as well. Now, this line is known as dislocation line that separates the slipped and non-slipped part. So, now if we try to look at in our actual diagrams or actual illustrations, so what happens when a dislocation moves? Now, in this first illustration, what we see, it is a perfect lattice structure, there is nothing, and then we apply some sort of force in this lattice above this line, which we will refer as glide plane. Now, initially when we apply the force, we will certainly push the crystals or atoms, I am sorry, the crystals on this side. So, these crystals will move a little bit. Now, here comes the very interesting part. Now, it can happen that all atoms in this area, it can receive the stress, they can move at the same time, and they end up by slipping each and every plane to give you a shape like this, which we will see is going to happen at the very end. But if you have to do it at one time, the stress you require is significant, and experimental studies showed that the actual stress that requires to deform is few orders of magnitude less. So, there must be something happening, or the lattices are accommodating the strain or moving the stress such a way within themselves that reduces the strength of the rock, yield strength of this system or the crystal. Now, this is how it happens. So, what happens that this line of atoms, they move, but then they displace a single set of atoms as well. So, therefore, it does not have any connection at the bottom, and this is where we produce our first dislocation or the cut that we talked about in the previous slide, that before this the material got slipped and after that it is unslipped, and then this dislocation moves one after another, and finally it achieved to this shape where we actually see that an unit length has got displaced. Now, this is how this slipped and unslipped lengths got changed continuously, and finally we get entire top part slipped, but it did not slip in a single process, but step by step. The movement of dislocations is very similar the way silkworms move or the way earthworms move on the surface. Okay. So, if we try to look at in a different way this dislocation. So, imagine that this is our dislocation line, this blue line here, and then this is our glide plane, and this unit vector that the dislocation moved on the slipped side along the slip plane is an unit vector, and it is known as Burger's vector. So, Burger's vector is the magnitude and direction of the unit slip. Now, this Burger's vector, the spelling is very similar, B-U-R-G-E-R, that we eat as a snack, is absolutely different to that what we call Burger's vector. Burger's vector is named after a Dutch scientist, physicist, his name is Jan Burgers. So, do not confuse these burgers to what we eat burger. Now, this is the plane along which we have that separates the slipped and non-slipped part. So, if we can project this plane in a flat area, then we see that this is the dislocation line. So, we are projecting this area on this surface. So, the yellow side is the slipped plane, and this light pink is our non-slip plane, right. So, this part got slipped and this part got non-slipped, and what is separating slip and non-slip is the dislocation line. Now, dislocation moving along this direction with the unit vector, unit Burger's vector. We can introduce another vector here, which is T, that tells about the unit vector tangent to the dislocation line. Now, in this case, this Burger's vector and this tangent vector are perpendicular to each other. When they are perpendicular to each other, this is known as edge dislocation, or the propagation direction of the Burger's vector or direction of the Burger's vector is perpendicular to the dislocation line. Now, here is an example what we see, that therefore, this B and T, their directions, their vector directions could have any angle, right. So, between the Burger's vector, which is the magnitude and the direction of the slip, and the line vector T, which is the unit vector tangent to the dislocation line. So, as we learnt that if B is perpendicular to T, then we call it edge dislocation. If B is parallel to T, then we call it screw dislocation, and if B is neither perpendicular not parallel to T, then it is mixed dislocation. So, what we see in this illustration, this is what we have learnt, this vector where B is directed this way and T is directed this way, their mutual relationship is perpendicular. So, this is my edge dislocation. But here, as we see that B and T, these two are parallel to each other. So, this is screw dislocation. Now, if there is other relationships like for mixed dislocation, then they form something called dislocation loops. You just learn the term, we will not go much detail of this. Now, this is how they look like if we try to draw them. So, edge dislocation is something like this, and now we know that it is defined with this T either flipped or straight, where screw dislocation looks like something like that, where the dislocation is moving in this direction, and here dislocation is moving in this direction for edge dislocation. Here are two models that you can see. This one is edge dislocation, I am sorry, this one is a screw dislocation, and this one is the edge dislocation, where this is the rotation axis and here this is the dislocation line. Now, the event does not matter whether we are dealing with edge or screw dislocation, the end products or the slip more or less they appear very similar, at least we understand for our lectures this way. They could be very complex, but we understand it this way, that when we have edge dislocation, this is the propagation direction and this is the dislocation line. So, they are perpendicular to each other, but because it continues to move, so eventually get a slip of unit vector Burger's vector. But here it slips this way. So, propagation direction of the dislocation is this and it also moved in this direction. So, they are parallel to each other, but eventually we end up with this Burger's vector. Now, does not matter, at least from a very basic idea we can have these diagrams in your mind, that does not matter whether this is edge dislocation or screw dislocation, we end up with the same type of deformed structure for our basic understanding, but actual thing is much more complex or it could be even complex. So, let us talk about that how do these dislocations move from one side to another side of the crystal. We had a very basic idea when we saw that one atom is moving relative to the next. We saw also the movement of the vacancies. So, one vacancy moves and then one atom moves to its opposite direction, but for dislocations, as we have understood so far, that it has to move along a particular crystallographic plane or what we have learned as a glide plane. Now, not necessarily dislocations could move along the glide plane always, life is not always happy. So, sometimes on the glide plane we have some obstacles in the form of interstitials, and the interstitials are sometimes so big that dislocations, individual dislocation do not have the energy to move or to sort of ignore these obstacles and move further on the same glide plane. If that does not happen, then it has to find one way to move to another glide planes and move accordingly. So, when it moves along a single glide plane, it is known as dislocation glide, motion of dislocations along a crystallographic direction. What we see here, that it is gliding on a single. So, these are your individual glide planes stacked in a crystal. Okay. Now, a climb happens when you have an obstacle which is impeding their glide motion, it stops the glide motion and it allows the dislocations to jump to another crystallographic plane and then continue glide. So, this is glide, then climb, glide, another obstacle, then again climb and then it glides again, and this is how it occurs continuously. Now, you clearly understand at this point that glides requires less energy than climb, because it has to climb, so it requires some more energy, and energy can come from various sources, we will learn about it later. So, eventually if I look at in a different form, it looks like this. So, this is the glide entire place. So, you see a fixed crystallographic plane and the dislocation is moving from one array of atoms to another array of atoms without changing the crystallographic plane. But here in this case we just see in a different way that probably here there was an obstacle. So, the dislocations moved to the next level and it changed its glide plane and continued moving as we see here. So, this is how the dislocation glide and dislocation climb are conceived. Now, let us talk about the surface defects. Surface defects are classified in two segments, one is external surface defect and another is internal surface defect. we won't talk about much, or we won't consider the external surface defects, but just to know that if atomic bonds are broken over an area, then you create two free surfaces and the area is double of the area you had. It has some other implications, but we are not going to deal with this, but we are mostly concerned about internal surface defects. And within the internal surface defects, we can have surface defects between the same phases and between the different phases. Between the same phases, we have grain boundaries, tacking faults, twin boundaries, and so on. And we also can have grain boundaries within different phases, and also a different kind of interface boundaries. So, from now on, we will mostly look at grain boundary, and twin boundary is also kind of grain boundary. We will look at mostly these two. We will ignore stacking fault for the time being. So, what is grain boundary? We all talk about that the grain boundary is straight, grain boundary is curvy, grain boundary is serrated, and so on. But from the crystal point of view or crystallographic point of view, a grain boundary is a boundary between two regions of identical crystal structures if we are dealing with same phases, but different orientations. Now, here we have two examples. This is iron oxide and this is calcite. You see that they are compositionally they are very same, but because they are differently oriented, maybe this grain here is oriented differently compared to this grain here, and this is why probably we see some lines in between them. We see different colors here. This is cross polar, this is calcite. Through cross polarized light, this is a thin section, and we see different colors. Because the grains are oriented differently, we see different colors. This we have learned from our optical mineralogy classes or mineralogy classes. Now, when we talk about different orientations, there are possibilities of various orientations from 0 to 90 degrees or more. So, we classify them mostly in two categories: low angle grain boundaries or LAGB, or high angle grain boundaries or HAGB. There are also a classification tilted and twisted grain boundaries. We are not going into that right now. Now, low angle grain boundaries, as it suggests that one grain orientation can be obtained by rotation of another grain across the grain boundary about an axis through an angle. So, that means I have, for example, two grains. Now, if my finger traces are the lattice orientations or so on, then they can have differently oriented by this angle, and this is the rotation axis. Okay. So, if this angle is low, then this is low angle grain boundary. If this angle is high, then this is high angle grain boundary. But how they look like? So, these are low angle grain boundaries. I have given two examples. As you can see that this probably is defining one very low angle grain boundary, where this and this two different areas or two different lattice structures, I am not saying the grains them yet, but their angle is only 4 degrees, very less. So, these are known as some sort of subgrain boundaries. Where the angle between the two grains are very, very less. And here this is also a subgrain boundary with more with higher grain boundary angles. And what is important, that this could be probably your grain boundary. What is important, that these grain boundaries are marked by dislocations, and if we have dislocations at the grain boundaries, that means the grain boundaries are also a storage or a places where you can find more or more dislocations. Then high angle grain boundary, as you can see here, this is your grain boundary, and in this case the grain boundary angle or high angle is 40 degrees, therefore this is high angle grain boundary. Now how high you need to make a high angle grain boundary or how low you need to make a low angle grain boundary, that varies from studies to studies, but generally 15 degrees or low is low angle grain boundaries and 15 degrees or above is high angle grain boundary. That is more or less the convention, but sometimes this 15 degree shifts to 10 degrees and so on. Now there is another type of grain boundary which is known as twin boundary, when two differently oriented crystals, so it has a grain boundary, but they are attached together such a way that they share some of the crystal lattice points in a symmetrical manner. What we have seen in other images, for example, if we come here, the previous slide, the lattice of this grain and the lattice of this grain, they are not sharing any of the atoms of the neighboring grain, but if it is a twin boundary then they share. So this is the twin grain boundary. Okay. So they share, so this line of atoms are shared in both grains, and if that happens then this is a twin boundary. Twin is very common in most of the geological minerals. For example, this is a sketch of an albite mineral. So this is a crystal without twinning, and these two blue planes are your twin planes and these are your twin boundaries. Now twin boundaries we can also classify in two different ways. One is contact twin boundaries or contact twin planes, and penetrative twin boundaries or penetrative twin planes. So contact twin boundaries, they share a sort of single composition surface, often appearing as a mirror image to each other. For example, we see here a quartz or this is a lazulite, but in penetration twins the individual crystals have the appearance of passing through each other, like they sort of penetrate one crystal, and of course it has to be done in a symmetric manner. So here are two examples. What we see here, this one is for pyrite and this one is for staurolite. As you can see from this, it seems that it almost went inside the crystal, but that happened in a symmetrical manner. So this is how we conceive so far a grain boundary. We have seen probably under microscope different crystals, their grain boundaries and so on, but actually if you can scan it or if you can X-ray it with some inner eyes, then the individual grain boundaries are like this, these blue lines, and they are separated. Even if their compositions are very similar, they are separated because their orientations, for example, here the orientation is like this and here the orientation is like this. So they are essentially different. For example, here the orientation is like this and here the orientation is somehow like this. So they are somehow different, and that is why we see them in a different way. Now this grain as it appears here, for example, if I consider these grains is extremely homogeneous. There is no dislocation inside in this area, there is no vacancy inside, there is nothing. So it is perfect, but that is not the case always. So this individual place can also be deformed, it may have also some sort of subgrains and so on, and therefore we see different kinds of features. For example, undulose extinctions in quartz, we will learn more about it soon. So we are at the end of this lecture. So I believe with this lecture you are now more or less convinced that whatever deformation we see in rocks, particularly in ductile domain of reformation, they all initiate at a very, very micro scale, in atomic scale. Now how to feel them, how to understand that yes, these are there because they are in atomic scale, and unless you have some sort of very, very high resolution microscopes like TEM or so on, you do not see them. So in the next lecture actually we will see and learn what are the different expressions of such atomic scale deformations and their typical arrangements and what are the different kinds of microstructures which are responsible for all these arrangements and deformations. So, this is the topic in the next lecture. We will divide it in 3 segments. The first we learn cataclastic processes, that is not really some sort of some study that involves all these things we learned, but this is very important in structural geology. But then we will go to intracrystalline deformation and diffusion creeps, where these things that we learned today would be very important. So, till then, goodbye, thank you.